Momentum, inertia in motion, moving mass, a mass in motion. One of the hardest things about momentum is the fact that we need to use the letter, or we will be using the letter P for momentum. The letter M has been overused already, or has been used for mass and mega and meters. So there seems to be some Latin word for momentum that starts with the letter P, so somebody thought it'd be a good idea to use lowercase p for momentum. In this case, we're talking about linear momentum, something going in a straight line. There's also going to be rotational momentum later on. But linear momentum can be calculated by multiplying the mass of an object times its velocity, as you see in this red box. M, the mass, we want that in kilograms, the velocity in meters per second. Therefore, the momentum, the linear momentum here, comes out in kilograms meters per second. And that's what we're going to stick with. We don't have an abbreviation or a shortcut for that. Momentum is a vector. It has magnitude and direction. We'll keep track of that with the examples. So that brings up a question. Does a freight train have more momentum than a tennis ball? Well, usually it would, but it depends. The answer is that it depends. Depends on how fast they're moving. Once again, if they're both moving, more than likely the freight train is going to have way more momentum than a tennis ball because it has way more mass. But, for example, if the freight train's not moving at all, it has no momentum. It still has mass, but it has no momentum because its velocity is zero. And if the tennis ball is moving at all, it will have some momentum that's more than a non-moving freight train. Even if the freight train's moving, if the tennis ball for some reason was moving extremely fast, it could still have more momentum than the freight train, but that had to be moving very fast. The law of conservation of momentum is very similar to the law of conservation of energy. It implies, once again, that something is not changing. In this case, with no external forces, the net momentum of a system does not change. So along with its counterpart, the law of conservation of energy, these are the two main conservation laws that we will be using this first semester of this high school physics class. Now, elastic collisions. There's two types of collisions that we will have that will apply the law of conservation of momentum, along with explosions that I'll show you here in a few minutes. But elastic collisions are collisions with no kinetic energy loss. No kinetic energy loss. They are collisions where there's a very bouncy effect. For example, if you drop a rubber ball to the floor, it has an elastic bounce. It bounces very high. Now, it's not a perfectly elastic bounce. If it were a perfectly elastic bounce, a rubber ball would bounce to the same height it started with. So there's always, in the real world, going to be some kinetic energy loss. But if there's no kinetic energy loss whatsoever, we would call it perfectly elastic. In this case, a bouncy ball in the real world is on the elastic side of the spectrum, but not perfectly elastic. The only place where you can get perfectly elastic, as you'll see here in a few minutes down a little bit lower, is essentially in the microscopic world. I'll circle that down here, where you have like air particles bouncing off each other in gases and things like that, small molecular size atoms bouncing off. They're even maybe not perfectly elastic, but real close. Then we have inelastic collisions in which some energy is transferred to heat. In the real world, there's always some energy transferred to heat, but if there's just a small amount transferred to heat, we still call it an elastic collision. It's on the elastic side of the spectrum. I'll show you that in a few minutes. So in our macroscopic world, all collisions are at least somewhat inelastic. There's almost always, well, there is always some energy transferred to heat. One last concept to define here, and that is impulse. It's the product of force and time. Equation-wise, it's here. And once again, we use the letter J for impulse, which seems like not a good letter to use, but using the letter I is problematic as well because it sometimes looks like a 1, but a lot of books do use an I. Some books use I, some books use J. I'm using J here. Impulse equals average force times time. An impulse will change the momentum of an object. The force here will be in newtons. The time is in seconds, so impulse is in newton seconds. I'm not going to spend any time proving this right now, but a newton second is equivalent to a kilogram meter per second. All right? It's the same units as momentum. So momentum and impulse have the same unit, and they're connected. And they're connected by this equation right here, J equals delta P. So J equals delta P. Impulse changes the momentum, and it's equivalent to the change in momentum. Make a note that J does not equal momentum. it equals the change in momentum. I'll give you some examples here. Actually, that'll be example number 4. But let me start with a conservation of momentum example. So applying the law of conservation to collisions and explosions. Here's a collision example. What you'll see as I do these problems, or as you do them, it's very important that you delineate a before and after the collision, or a before and after the explosion, whatever it is, a collision or explosion. Here the scenario is you have a bumper car, like at a county fair or at Great America. Overhead view. You have one car traveling towards a stationary car. It's going to bump into the back end of the stationary car. The heavier car, the 280 kilogram car, is moving at 4 meters per second towards the stationary car. So there's the diagram. What you want to do in these problems is draw this out. These are not really free body diagrams per se. We want to focus on the momentum. And the way I do it is I call this P1 equals M1 V1. The one here all represents this particular car before it hits the second car. And then we have P2 equals M2 V2, car number 2. Well, car number 1 is moving, but I've been given the mass, 280 kilograms, times the velocity, which is 4. So the momentum of this car is 1,120 kilograms meters per second towards the right. Now that's an important number. I'm going to circle it. It's towards the right, but we can see that in the diagram. And P2 equals, well, 210 times 0, so it's 0. 0 kilograms meters per second. That has no momentum. It's not moving. What's important is P1 plus P2. Now, when one of the objects is not moving, it's real simple. 1120 plus 0 is 1120. So what's important here is you add those two. I get P total. Sometimes they're both moving, so you have to add them up as vectors, as you'll see in the next example. But P total here is easy, 1120 kilograms meters per second. That's what is conserved. The blue thing is what's conserved, not either one of the red items or red momentums, because individual momentum can change, but the system momentum cannot change. So you set the problem up, you figure out what the momentum is before the event. Then you go to the after the collision, and I'll draw that. I've drawn the after the collision scenario. The little guy is shot off at 3 meters per second to the right, and we want to find the velocity, the new velocity of the 280 kilogram car, which will be less than it was before. So what I like to do is I'm going to call this P3 equals M3 V3, representing the bigger car after the collision, and then P4 equals M4 V4. Well, I know M4 and V4, so I have to start over here on the right. P4 equals the mass of that car, which is 210, times the 3. I'm going to squeeze that in. So P4 is 3 times 210, which is 630 units. It's kilograms meters per second. Squeezing that in there, of momentum to the right. Now I must have a total of 1,120 kilograms meters per second of momentum. What this looks like mathematically then is P3 plus P4 must equal the 1120. And we know P4 now, well, P3 plus P4 is 630 equals 1120. So P3, the momentum of the large car after the event, must be 490 kilograms meters per second. And we know from above, up here in blue, bring this down, if I plug into that equation that I'm bringing down here, I know that P3 is 490, so therefore, well, I'll do it in blue, I'm going to have 490 equals mass number 3, which is 280 kilograms, times V3. So by dividing, I end up with V3 equal to 1.75 meters per second to the right. The direction is not real important in this problem, but to be consistent, that is the direction as illustrated in the diagram. Alright, so that's the answer to part A. We need the velocity of the large car after the collision. Now, part B, to find the kinetic energy that may have been lost. I'll do this in black now. There's quite a bit of work to be done here. I need to find the kinetic energies involved. For example, KE1 will represent the kinetic energy of the big car before it hits the little car before the collision. So that's simply going to be 1/2 m1 v1 squared. So if we just plug that all in here, KE1 is 1/2 the mass of that car, which is 280 times 4 squared. So the kinetic energy of the large car before it smacks the small car is 2240 joules of energy. Alright, now KE2, the small car before it got hit had 0 joules of energy. So the total energy before, KE total, okay, 1 plus 2, before the collision is the 2240 joules. After the collision, I'll do this to the right here, KE3, which stands for the large car after the collision, is 1/2 the large car, 480, that's its mass, times its post-crash velocity, which we just found is 1.75 meters per second, squared. So if we plug all those numbers in there, that comes out to be, I believe, 735 joules of energy for the large car after the collision. KE4 is equal to 1/2 the mass of the small car, which is 210 kilograms, times its post-crash velocity, 3 squared. Make sure you square that. So KE4 comes out to be 945 joules. Alright, so now if I take the KE3 plus the KE4, that's this 735 joules for your KE3 plus your KE4. Those two numbers are the kinetic energy after the collision. Those come out to be 680 joules. If you look at the ratio of 1680 joules left over out of the original starting pre-crash kinetic energy of 1 plus 2, which is the 2240 right up above here, that comes out to be 0.75, which is 75% of the kinetic energy is retained. Therefore, 25% of the KE is transferred to heat, is lost, quote unquote, transferred to heat. Now, that's not a big number. That's the answer to part B. So part C then, is this elastic or inelastic? Well, it's not perfectly elastic, but I would say it's somewhat elastic. Now, that's a little vague, but the number 25% is what I will look at when I grade these on a test. That's showing you numerically or quantitatively what's going on here. It's a relatively small amount of kinetic energy lost in the scheme of collisions. So it's on the elastic side of the spectrum.